Welcome to the FAA Production Center and the FAA Safety Team National Resource Center located right here on the Sun and Fun Complex in Lakeland, Florida. I'm your host, Walt Schammel, and our next presenter is a corporate pilot from Northern Illinois. He has over 5,000 hours and an ATP with type ratings in Learjet and citations. He's also a Gold Seal flight instructor in airplanes, instrument, and multi-engine. His aviation career is very varied. He's a flight instructor, a charter pilot, corporate flying. He was a TV weatherman in Southern Illinois and holds a master's degree in aviation. He's a member of the Chicago Flight Instructors Association. He's well-respected aviation safety speaker throughout the United States, including at EA Air Adventure and right here at Sun and Fun. His topic today is surviving forced landings. Let's welcome Eric Basil.
Thank you very much, Walt. Good morning and welcome to Sun and Fun. I'm thrilled to be back here again. Of course, when I left Chicago to come down here yesterday, it was about 50 degrees and the rain was blowing sideways, so they really didn't have to twist my arm too hard to get me to come down here. I'm talking about a little bit of a serious subject this morning. To many pilots, it may be your worst nightmare, the prospect that you'll be flying along fat, dumb, and happy, and all of a sudden something will go wrong with your engine. Or even worse, you might have just taken off and then all of a sudden the engine will backfire or stutter. Something that a lot of people don't want to think about. But my hope is that you will come away from this morning a little bit more mentally prepared and a little more enlightened about how to handle this emergency should that ever happen to you. We're going to review some of the fundamentals of making a successful emergency approach and landing, as well as talk about some unique characteristics that you may not have read about or you may not have thought about in a particular way. So we're going to review some of the keys to making a successful forced landing. And the first is proper pre-flight planning. And we're going to look at how knowing your environment will make for a much more successful outcome if you ever had to make a forced landing. Next, we're going to talk about the importance of understanding airspeed and how there's not just one airspeed to fly in an emergency situation. We're also going to talk about coping with stress because, after all, an emergency landing is a very stressful situation, and it's important to understand how stress works and how it's going to affect your performance in an emergency. Next, we're going to discuss the importance of knowing your airplane and how to get the maximum performance out of your particular airplane if you ever had to make an emergency approach. We're going to talk about approach and impact management, which is something that's not really discussed all that much, but it really is very critically important to making sure that you have a successful outcome if you ever had to land your aircraft off of an airport. And finally, we're going to underscore the importance of practicing your skills. Now, I'm going to start out with a little bit of a rhetorical question. I like to start out my presentations with a rhetorical question because I don't want people to think that accidents just happen to other pilots and it can't happen to me. I want you to understand that this could very well be you in your daily flying. And so these keys are just as important to you in the type of flying that you do as they are to other pilots. Now, this is a little bit of an older accident, but it's still very valid. It was in central Illinois. A gentleman was taking off and flying in a Piper Cherokee 6, and I use this accident case because these folks were taking off and they were flying to Oshkosh. So it was a very similar type of situation as what some of you have may did coming down here. They took off from a private strip. Lost power on takeoff. One witness said that he heard the engine backfire and then lose power. The airplane was in a slight turn and stalled in the turn with, unfortunately, 2 fatalities. Now, the probable cause from the NTSB is fairly lengthy, but I will highlight the fact that it says that there was an incorrect fuel tank selector position and the aircraft stalled in a turn. Perhaps most importantly, though, the observations of the surrounding farmland reveal that there were plenty of suitable areas for a forced landing. So unfortunately, due to the pilot's desire to return to the airport that he took off from, he ended up stalling in the turn and causing a fatal accident. Now we're going to focus I'm going to frame this discussion when we talk about forced landings. I just want you to understand the FAA's definition is that it's an immediate landing on or off an airport because you couldn't fly any further. So it's differentiated from a precautionary landing where the engine might still be making power, but you chose to put it down. This would be you have no power and you need to put it down because it's not going to continue flying. Let's talk a little bit about some engine failure causes. Now, you may notice that this is from calendar year 2000. You might ask, why am I looking at the year 2000? Well, a couple reasons. One, the year 2000 is sufficiently far in the past that all of the accidents that occurred during that year have been thoroughly investigated and probable causes have been determined. Secondly, the year 2000 was prior to 9/11, and so it represents a year where the economic activity in the United States was good, and consequently the level of recreational flying was also representative of an average year of flying. There were 400 engine failures in that calendar year. This removes failures of experimental aircraft and agricultural aircraft. So we're just looking at certified aircraft. And you can see the distribution very sort of disproportionately is made up of fuel mismanagement. Fuel mismanagement represents three possible things. The first is fuel exhaustion, which means that there was no fuel left on board the aircraft at all. The fuel was completely exhausted. There's fuel starvation, which means that there was fuel available somewhere on the aircraft in a tank, but it wasn't accessed either because the tank was set, the selector was set to the wrong tank, or the selector was malfunctioning. And lastly, we have fuel contamination. So those three causes make up what we call fuel mismanagement. And so the first point that I'd like to make is that you can see that the bulk of engine failures are not what many of us would conventionally think of when we think of an engine failure. Most of us would think, oh, an engine failure was caused by some sort of mechanical problem, when in fact almost 50% of them are caused by fuel problems in one way or another. Next, we also have improper maintenance, which is either faulty parts used at overhaul, or there was some sort of procedure that was not followed properly by the mechanic when overhauling the engine or repairing it. And then we have about 6% of the accidents that were caused by carburetor icing. So what's the overall point that I'm trying to make here? Well, you can see if you look and you group all of these three things together, you can see that well over 50% of engine failures are related to something that is in one way or another directly controllable by the pilot. If you make sure that you have fuel on board and that your fuel system is properly maintained, if you make sure that your maintenance is done properly at an approved facility using approved parts, and you keep a watchful eye for carburetor icing, you've immediately removed well over 50% of your risk for having an engine failure. And so you have to keep in mind that if you do these things and you're reasonable about your pre-flight planning and so forth, you've dramatically cut down your risk right there. Now, what we have left is a segment related to unknown, because either the aircraft was lost at sea or some other reason where they were unable to determine what happened. And only about a quarter of the engine failure accidents were related to what we would conventionally think of as a mechanical failure, like a crankshaft problem or cylinder problem. So that's kind of my first point, is that only about a quarter of the accidents are what you think they would be. And my second point is that if you put all of these together, these 360 accidents, only 10% of them were fatal. And so the other point that I'd like to make is that just by the fact that you've had an engine failure doesn't necessarily mean you're going to have a fatal problem. There's really no reason at all for just a simple engine failure to result in a serious or fatal accident. And so part of your defense here is going to begin well before the flight by making sure that you do a proper job of pre-flight planning. So when we're talking about pre-flight planning, the first thing is the importance of knowing your terrain. Now, we have here a couple segments of some sectional charts, and you can see pretty clearly that there's a difference between the two. How would you approach your flight planning and your conducting your flight if you were flying in this area as opposed to this area? I mean, clearly this is a mountainous area, so it would probably behoove you to fly at a higher altitude to give you a little bit more decision time if you had a problem. You could also choose to plan your route of flight so that it follows this interstate highway, which is probably in a valley area, or there's a little bit more of a clear area, a little bit more populated area if you needed to put the aircraft down. You could also plan your flight so that it bears more closely towards airports, so that you would have places to turn to if you needed a problem. Now, in this area, it's a lot flatter, there's a lot more open space, so you have a lot more alternatives available too, but this shouldn't mislead you into thinking that you're totally fine. You should still plan your flights so that you have options available, that you've considered terrain and obstacles along your route of flight. So the first things that I'd like to counsel you on is first, don't become GPS dependent. I tell a story every time about the gentleman that took off from Bozeman, Montana in a 172, and he's headed out to the Midwest. And he calls up Salt Lake Center for VFR flight following. And he says, Salt Lake Center, this is Cessna 12345. I'm at 11,500 feet, request flight following. Salt Lake Center says, say your position. And the guy says, oh, I'm 863 miles northwest of Lincoln, Nebraska. And so the controller said, well, do you have anything closer? So that is an indication of somebody that is borescoped on their GPS, and they've just put direct to their destination, which is fine. GPSs are great, but the idea is, instead of just following that magenta line wherever it's going to take you, you should have some understanding of the type of terrain and what's beneath you, and rather than just flying that shortest possible direct line to your destination, maybe you could go direct to a few waypoints along the way, maybe alter your course just slightly, 10 or 20 degrees either side as you go along, so that you're closer to one airport, you're closer to another airport, or maybe you don't go into this area where it's really remote or mountainous. And so by doing that, following the magenta line on your GPS, you're going to lose your situational awareness of what's underneath you as you fly along. And that's half the battle of understanding what's going to be safe and what's going to be unsafe if you were to lose power. So some suggestions to counteract that. First of all, you could use a sectional or a website called aeroplanner.com to study your route beforehand. How many folks here are EAA members? Raise your hand. So those of you that are EAA members, you have a free subscription by virtue of your EAA membership. You have a free subscription to aeroplanner.com. And you can go onto this website, type in your route, and you can display a route of flight on any type of map that you like. A WAC chart, a current sectional chart, IFR and route charts. It lets you lay whatever you like under it. It'll have your course line drawn on it with mileage markers. And most conveniently, you can print out little kneeboard-sized pieces of sectional map, so that rather than folding and unfolding this big sectional map in the cockpit, you can just look at these little squares and flip through them as you go along, and it's going to show you what's either side of your route of flight for about 30 or 40 miles either side of your course line. It's a great idea to use so that you say, okay, here's an airport that's maybe 20 miles off to the right. If I needed to go, if I started to lose power or something was going wrong, I could divert to here. Next, study your local airport area once you get to where you're going. I've done this, I'm sure you have too. Once you get to the airport, your destination, where's your mind? Your mind has already landed the plane and is thinking about what is lying ahead of you at your destination. Either you're there to visit family or you're there for business. Your mind has already completed the flight and is thinking about what's ahead of you. But what you should be doing is, if it's an unfamiliar airport that you've never been to before, as you're coming in to do the traffic pattern, take a visual survey of the area around the airport, and you might notice, gee, off the departure end of the runway, there's a nice big clear area just to the left. Or there's a big Walmart parking lot off to the right. And so that way, if it's an unfamiliar airport, you can take off feeling comfortable that you know what's ahead of you, rather than being in a situation where you're only 200 or 300 feet off the ground and all of a sudden you're in a problem and you have no idea what's there. So you can study the local airport area on arrival. Another good technique is to use Google Earth, which is also on the internet, because you could type in an airport location. It'll zoom right in on the airport, and you can see a nice satellite picture view of the terrain and development around the airport. As I've mentioned before, you should plan your routes as best as possible to provide a suitable landing area. Consider the terrain, consider remote areas, and also consider increasing your altitude to provide greater gliding distance and give you more time to try to fix the problem or declare an emergency and request help. So once you've done these pre-flight planning steps, we are in the airplane. Unfortunately, we're in cruise. Everything's going okay. Now the engine's starting to make trouble, or it just quits completely. What's the absolute first thing you need to do? You need to establish a glide. And this is a problem for people because pilots by nature are somewhat problem-solving individuals. And so when something starts to go wrong, what's our first impulse? It's to try to fiddle with stuff to try to make it go away. And so rather than fiddling with fuel selector or pump, the first thing you really ought to be doing is establishing a glide. Even if the engine is still running, you can slow the airplane down or establish a pitch attitude that's going to establish a glide, trim the airplane so that it will hold that by itself, and then you can start to focus your attention away from establishing the glide. But if you don't do that first of all and you start fiddling with things beforehand, you're probably going to be trading away altitude that you needed uselessly. So once we've established that glide, let's talk a little bit about a glide. Everybody knows best glide speed. It's kind of a subject that's mandatory for private pilot training, so everybody's talked about it. What does best glide speed get us? Well, the definition of best glide speed is that it's going to obtain the greatest forward distance per unit of altitude lost. Okay? So the bottom line is it's to go far. That's the speed that you want to fly at if you need to glide to something far away. Now there's a couple hitches though with this concept of best glide speed. The first is that it's typically only published for the maximum gross weight of the airplane. What's the problem there? Well, how often are we flying at maximum gross weight? Often we're not, especially if we're flying just alone with half tanks or three-quarter tanks or something like that on a pleasure flight. Of course, legally, there's only one moment in time where you can be at maximum gross weight, and that's sitting on the runway getting ready to take off. As soon as you've burned one drop of fuel, your weight is starting to go down. And so understand that that's typically published for only maximum gross weight. And the key is that if you're flying at a lighter weight, your speed is going to change for best glide. And I'd like to show you just a small formula that's going to show you how to approximate the best glide speed if you're flying at anything less than maximum gross. Now, let me preface this by saying this may look complicated. I am not the world's greatest mathematician by any means. In fact, I could not tell the difference between a quadratic equation and a ham sandwich. So this is the most complicated mathematics that you will ever see from me. I promise you that. Now, the formula to approximate best glide speed is you're going to take the best glide speed that's published for your aircraft at maximum gross weight. And you're going to multiply it by the square root of whatever the quotient is but of your present weight divided by the maximum gross weight of the aircraft. So let me give you an example. We're going to take a prototypical light GA airplane that has a best glide speed of 65 knots at max gross weight. We're going to say that that aircraft's maximum gross weight is 2,400 pounds. Except we're not flying at 2,400 pounds today. We're flying at only 1,800. Let's say I'm flying by myself and I don't have full fuel. Okay? So divide that out. That gets you 0.75. And we're going to take the square root of that and multiply it by 65, which gives you 0.866. Multiply that out. That gives you 56 knots. Now, would you agree that there's a difference between 56 and 65? Okay? What's going to happen if you're flying in this situation and you glide the plane at 65? It'll glide fine. The only problem is that you're going to needlessly trade away altitude for no reason, and you're going to end up landing shorter than you would if you actually glided the plane at the proper best glide speed. That would get you maximum range. Are we clear on that one? Okay. I'll leave that up for just a second so you can copy it down. Now, if you happen to be flying a plane where you don't exactly know what the published best glide speed is, it's probably going to be very close to whatever your best rate of climb speed would be. Because in both cases, you're looking at L over D max, basically. Now, more importantly than best glide, I want to introduce another concept to you, which is called minimum sink airspeed. Now, everybody has heard of best glide. You get tested on it on your private pilot check ride. When you do an engine failure, you need to know what best glide is. But very few people understand what minimum sink airspeed is. And what I want you to understand is minimum sink airspeed is just as important in an emergency landing as best glide speed is. Because as we said, what is best glide speed going to get us? It's going to get us far, right? Minimum sink airspeed is to be used when range is not important, but time in the air or endurance is. Let's say I have an engine failure at 5,000 feet directly over an airport. Well, what's important to me? Is it gliding far, or is it staying in the air as long as I possibly can to try to get the situation taken care of? Make sense? So in that case, rather than glide at best glide speed, we're going to try to glide at minimum sink airspeed. Now, one way that you can try to approximate that in an airplane is in many airplanes, if you put a power off situation and you crank the elevator trim all the way to the nose up stop, the airplane will eventually porpoise slightly and then it'll stabilize somewhere around that minimum sink airspeed value. But looking at it mathematically, what we do in a lot of cases is we do what's called a polar curve. So we're going to set up a little graph here. This would be vertical speed, positive and negative, and then this is airspeed. Okay, so here we are, 0 airspeed and 0 vertical speed, and here's 100, and we'll call it 120 knots. Okay, and the way this looks is something like that. Okay, and all we're doing is we're plotting what kind of descent we get at various airspeeds. So if we draw a tangent line from the origin to the curve, wherever that touches the curve, that's our best glide speed. Okay, and let's say that that translates to something around a descent rate of maybe, I don't know, 400 feet a minute. Okay, however, you see that the curve goes up a little higher, and it might be 300. And so this is the point where we call minimum sink airspeed. This is a concept that is very intimately familiar to glider pilots. Do we have any glider pilots in the audience today? Okay. Glider pilots know minimum sink airspeed because this is the speed that they fly in thermals. So when they're not flying, or when they're going between thermals, they go to best glide because that gets them further while they're trying to minimize the time that they're sinking. But when they're in the thermal, they fly at min sink airspeed because they're trying to stay in the air. They're not trying to go anywhere. And so this has application to you because if you're gliding and you know where your glide spot is, it's directly below you, slow the plane down to minimum sink airspeed. This may be 5 to 10 knots slower than the published best glide value. So if you wanted to test it in your plane, set up a power off glide, go to your best glide airspeed and see what kind of rate of descent you get. Slow the airplane down a few knots more. Let it stabilize, see what kind of rate of descent you get. Slow it down a few knots more, see what kind of rate of descent you get. Eventually you're going to reach some value where it's not sinking all that much, and then as you keep slowing, now of course the drag starts rising and it's going to start descending even faster. And so that's where you start to get to this back side of the curve here. But once you understand this minimum sink value, establish that in your mind so that if you ever needed to maximize your time in the air, you go to that minimum sink value. And that minimum sink airspeed is also going to be important when we start talking about energy. So if you need to approximate what minimum sink is, it's probably near your VX speed or your best angle speed. So the point that I'd like to make here is that we sort of need to eliminate the rote level of understanding of best glide speed. Barry Schiff did a column some time back where he talked about this exact subject. Barry Schiff was out in Seattle or something and needed to get checked out to rent a 172. He went up with a very fine young instructor who was very knowledgeable, but the instructor decided to simulate an engine failure for him. And Barry said, well, my landing spot is directly below me. I'm going to go to minimum sink airspeed. And the instructor went, oh, you need to glide at best glide speed. And that just simply isn't so. Minimum sink airspeed is important. It's a very critical speed if you need to minimize your energy and you need to stay in the air as long as you possibly can. Also, glide speed can and should be adjusted for wind. Glider pilots do it every day. But somehow this knowledge hasn't translated over to the powered pilot community. That if you're gliding into a headwind, you need to increase your glide speed to achieve better penetration into the wind. So the rule of thumb that glider pilots use is they increase their glide speed by about half of whatever the steady headwind is. And that's just to achieve the same amount of penetration into the wind. Now for a tailwind, you can slow down slightly, but not quite as much. How many folks fly an airplane that has a constant speed propeller with a propeller control? A couple folks in the audience here. The other thing that is necessary to do with a constant speed propeller is to make sure that you bring the propeller lever back all the way to the low RPM pitch stop. Because if you keep the propeller lever forward, the governor is still going to try to command high RPM, even though there's no power available. And so with that propeller windmilling away, it's just robbing energy from your glide. And so you could also set this up experimentally if you try this next time you're flying. Set the airplane in a idle power situation, go to a glide, pull the propeller lever all the way back, and see what kind of feeling you get. I mean, you feel like the plane is almost accelerating forward because you feel all that drag starting to go away. And so the situation that you see here with the throttle quadrant in the photograph, that would be the correct situation. Now let's talk about some characteristics of a good emergency landing site. Let's see, the first one, far away from the FAA, right? Does anybody else have some ideas of what a good landing site would be? We want a preferably 4-star hotel nearby, or a Walmart where we could change our shorts because we probably need to do that. Who has some other suggestions? Good emergency landing site. Into wind. That's an excellent suggestion. It should be into the wind. What type of area would you like to touch down in? Flat. Flat. Any other suggestions?
No wires.
Okay, good. No, okay, so it should be flat, no obstructions. How big should it be? Okay, I heard somebody say huge, but then I also heard somebody say sufficient. And that's an excellent answer. Sufficient. What is a sufficient landing site? How big does it have to be? It would probably surprise you. Unless the terrain is really, really severe, chances are that there is probably a suitable landing area nearby for you. You probably just wouldn't even consider it. Now, in my time as an instructor, I'd simulate engine failures for people, and they'd look way out on the horizon and they'd say, I'd like to land way out there. And so, for some reason, there's just this inclination among people that they look way far away out in front of them and they pick a big field, and then they set up best glide speed. Problem one is they may not reach the field. They may set up best glide and say, oh, all of a sudden I found out I'm not going to make it. So my instruction to you is to try to start to think about places that are a little bit closer into you, that's close by, that it doesn't necessarily have to be huge. Now, one technique you can do is you can go to your spinner visually and then think of an imaginary circle that's going from your spinner to your wingtips and then back to your tail. And picture yourself as being on top of a big pyramid or a big cone. If you're on top of that, in a no-win situation, you can glide to anything within that area. So start looking a little bit closer in for areas that you could glide to. And what's the benefit of doing this? Well, if you don't have to glide or cover as much distance to get to your gliding spot, that gives you more time to set up a good approach. It gives you more time to set up minimum sink airspeed so that you have a little more time to deal with the emergency, declare a mayday, prepare your passengers, get everything situated in the cockpit. Rather than spending all of your time in this long straight ahead glide to this far away spot and then, oh, I'm not going to make it. Also, don't forget the area behind you. Too many people, they only think of maybe what's in front of them and maybe slightly to the sides. But you may have just passed something that's immediately behind you. But the problem is, in an airplane and in a car and all these other things, humans are really forward-thinking individuals. We just kind of have blinders on and we just think of what's ahead of us. We're thinking towards the destination. We're thinking of getting to where we're going. doesn't even enter our thought process to turn the plane around 180 degrees and maybe we just passed something, a huge field immediately underneath us. Another trick that you can use is called the rule of thumb, and that's literally because it's a rule of thumb. The typical GA airplane glides at a ratio of about 10 to 1. Now, like a smaller aircraft like a 152 glides more at about 6 to 1, but a ratio of 10 to 1 is a glide angle of about 6 degrees. And so the neat trick is that if you stick your thumb out at arm's length like this, your thumb from the tip to your big knuckle on your thumb, that's 4 degrees. That's an arc of 4 degrees. And then if you just go a thumb and a half below the horizon and then figure out where that spot is, everything from that point in, you're going to be able to make it to. And so instead of just picking something way out on the horizon, use this rule of thumb, and then that gives you a better approximation of how far you're going to be able to glide given your altitude. Also want to talk about knowing your airplane. A couple folks here fly constant speed aircraft, so we talked, or constant speed propeller aircraft, so we talked about what you need to do with the propeller lever. But you should understand the best glide speed and the associated conditions that are required for that best glide speed. You should also understand what the emergency procedures and troubleshooting are for your aircraft and maybe develop what we call a flow check. Now this aircraft is a Piper Turbo Aero, and you'll notice that there's a whole bunch of associated conditions in order to get maximum glide range. First of all, we can see wing flaps up, obviously, 97 knots at 2,900 pounds gross weight, which happens to be maximum gross weight for this airplane. So again, if you're flying at any speed or any weight less than maximum gross weight, this speed is going to be consequently reduced. Gear should be up, power off, propeller to full decrease, of course, and 0 wind. And so then you could go into the table and figure out what your maximum glide should be. Now, this comes from the FAA's flight training handbook. And so your results may vary for your particular airplane. But of course, what did we say was the most important thing to do before you start troubleshooting? Establish a glide, okay? Then you can go through a fuel, check carb heat, turn your fuel pump on, and so forth, to make sure that you've done everything you can to try to fix whatever problem may have occurred. You could also use the acronym ABC. Airspeed, set your glide airspeed, figure out where you're going to land, and then turn your attention into the cockpit to try to rectify the emergency. We're going to talk about stress a little bit. This guy is having Excedrin headache number 285 here. Most forced landing fatalities, I think, are caused by a failure of the mind more so than they were a failure of the aircraft. If you can't wrap your mind around the fact that you're in an emergency situation and that your skills are going to be required to get you down safely, if you're in denial or you're worried about damaging your aircraft, then those things are going to override your rational thought processes with fear and consternation, and so then you're not going to be able to use your training to get yourself through the emergency. Many pilots just freeze up or they're indecisive, and the problem is when that panic sets in, you're not the PIC anymore. You're just a passenger on board an engineless aircraft. And so, Bob Hoover used to say, fly the thing as far into the crash as possible. You are the master of the aircraft. You are the pilot in command. You're responsible for getting the aircraft down and getting yourself out of the situation. How are you going to do that? You're going to use your training and your knowledge. And so you've had a problem with the airplane. They're rare, but they happen. And so once that happens, you need to figure out a good spot to put the aircraft and put it down without worrying about damaging it. Damage might happen, it may not happen, but you just can't be worried about that at that point in time. You have to worry about protecting yourself and anybody else that's on the aircraft with you at that point. Of course, we know there's a relationship between stress and performance. If I gave you a relatively uncomplicated task like sit you in a room with a button and a light bulb, and I tell you anytime the light bulb comes on, you need to hit this button, your performance would be fine. But if I asked you to do it for 8 hours, you'd probably get bored and your performance would suffer. So what am I going to do? I'm going to introduce a small amount of stress by way of inviting my friend Guido to come in, who has his newspaper, and any time that you fail to push the button at the proper time, he's going to slap you across the face. What do you think is going to happen to your performance then? It's going to improve. Well, if I just tell Guido to just slap you all day long without any regard for whether the light bulb was on or not, then of course your performance will start to suffer again. And so that's what we call being task saturated in an emergency. You're so focused on the fact that you're getting beat up that you can't even focus your attention on the task anymore. How do you deal with task saturation? Shed load. And so what are you going to focus on? You're going to focus on flying the airplane properly and doing the steps in order, following your training to get yourself down in one piece. And we see that in a complex task or emergency, of course, you get task saturated a lot quicker than you would if I gave you a simple routine task. So here we have a situation, you can read the caption here, it says, "The fuel light's on, Frank, we're all going to die. Oh wait, it's the intercom." So I would say this would be a poor response to a stressful situation. Here is a slightly better response to stress. He says, "Oh wait, there goes my hat." So the idea with panic is you could keep in mind the Air Force, what the Air Force teaches their pilots is to remember and memorize this statement: maintain aircraft control, analyze the situation, take appropriate action, and then land as soon as conditions permit. Again, the success of an emergency landing under adverse conditions is as much a matter of your mind as it is of the skills that you have. Now we're going to talk about managing the approach. I underline the word managing because managing is an active process. Okay? Again, if you lose the power and you don't do anything about it, you're just sort of giving up control of the airplane and becoming a passenger. This is not going to be a passive process where you just set the airplane up and let it fly itself. This is a process that needs to be actively managed all the way down to the ground. And so you're going to identify a landing site and you're going to maneuver the aircraft so that it's in a position to properly land. Closer in, what they have you do is just manage your approach using distance from the touchdown point as well as adding drag or slipping and then aiming to touch down at the proper airspeed. This comes from Kirshner. I bring this up because I have a little bit of an objection to this part that he put in here where he talks about overshooting it and then turning back. And I'm not really sure that that's a good idea to be doing that kind of thing at slow airspeed, especially where you might end up getting cross-controlled. We know how those end up. And so the idea is, how are you going to manage this? You're going to manage it all the way down by managing your distance, checking for the wind, managing your distance from touchdown, and looking at how much altitude you're losing to try to be in that position where you can touch down properly. Now, again, here's more math. I don't know how this crept in here. But this is the formula for kinetic energy. And this is kind of the part that I really want to hit on because this is something that I don't think a lot of people think about. You know, in a pilot training, it's just hold best glide, and then all of a sudden you get down to 500 feet and then they say, okay, go around. That's your simulated engine failure. But where I think people really have a question mark is from that point to 500 feet down to actual touchdown, because we never get to practice it in real life. But this is where you're really going to make or break whether you're going to walk away comfortably from this situation. And so we're talking about energy. Now, your ground speed at touchdown is critical. If you double the ground speed at touchdown, it quadruples the amount of energy that you have to dissipate in the rollout. And conversely, if you reduce your ground speed by half, that's going to reduce the amount of energy that needs to be reduced by down to 1/4. So what's the overall point here? Come in as slowly as you possibly can, because the less speed that you have coming in, the less energy has to get dissipated, the less distance you need to roll out for your landing. All that energy has to be distributed somewhere. It could be either distributed in your rollout or it could be distributed as you run into a brick wall. Which would you rather have? So the slower you come in, the more likely it is that you're going to be able to walk away comfortably from the situation. Even a small change in speed, whether it's because of your pilot technique or just because you went into the wind, that's going to affect the outcome. And so the gentleman that said land into the wind, you're absolutely right. It may be to your advantage to pick a less favorable landing site that is into the wind than it would be to pick a larger site where you would have a tailwind. because of that energy that needs to get dissipated once you touch down. Let's put some numbers on it. If you touch down at 85 miles an hour, it's twice as hazardous as you touch down at 60. It doesn't seem that way, does it? 85 doesn't seem all that much faster than 60, but it's twice as much energy. Also, 120 miles an hour is 3 times as hazardous as 70. So you can see a 10 mile an hour increase in speed doesn't really give you that much more energy, but you know, once you get to a really fast speed, it starts to increase proportionately. So let's talk about how big this area has to be. And here we have a graph of energy, and here's the polar curve that I drew for you before, and you can see where minimum sink would be relative to best glide speed, and you can also see what kind of energy you would have. Here's the energy you would have at minimum sink versus the energy you'd have at best glide. So even if you were gliding a long distance to something properly, okay, we're going to set best glide and we're going to fly this long way to glide somewhere, what kind of speed are we going to try to maintain once we get ready to touch down? Are we going to touch down at best glide, or are we going to touch down at minimum sink? We're going to use minimum sink. So properly, you should be using best glide to get to where you're going, and then once you are where you're going to land, slow to minimum sink and reduce that amount of energy. Now, GA aircraft, certified under the old CAR 3 regulations, were certified to protect you to 9 Gs in a forward direction. That means that the seat attach points and the seat belt attach points are stressed to retain you within the aircraft to an acceleration of 9 Gs. 1.5 Gs sideways and 6 Gs down. Okay? So, if you can decelerate the aircraft at 9 Gs, you'll be retained within the aircraft as long as you're using the harnesses and your seat is in good shape. And you should be able to decelerate the aircraft and walk away. So let's say you touch down at 50 miles an hour. How much distance do you need to decelerate the aircraft in a 9G deceleration? This would be, how many feet do you think it's going to take if you touch down at 50? 100 feet. Anybody want to give me a different number than 100? 250. Okay. 50 miles an hour, 9G deceleration, you need 9.4 feet. And this is survivable. How about at 100 miles an hour? I'm sorry, speak up. It's 37 feet. Okay? So what's the larger point here? The larger point here is that you don't need a 5,000-foot long open field to successfully accomplish an emergency landing. If you touch down and you struck the wing against something, what's that going to do? That's going to dissipate an enormous amount of energy through that impact, but it's going to dissipate it safely because it's a piece of the aircraft that you can sacrifice. It's not in the passenger cabin. If you struck a pole directly in the cabin, that would be bad, but if you struck a pole with your wing, that's going to dissipate a huge amount of energy, but you're still inside the cabin restrained by your harness, and then you can open the door and walk away once you're stopped. So that's the idea, is to figure out ways to dissipate energy safely, and you don't need a lot of distance to do it. So again, touching down during the emergency landing should be at the slowest controllable speed using all the aerodynamic devices that you have available. Now, this doesn't mean stall it in. Stalling it in is a big problem because now the aircraft is out of control. You're not sure exactly where it's going to impact. It could roll on its side or roll inverted, and the aircraft is really not built to land on those surfaces. But if you land on the landing gear and you use sacrificial pieces of the airframe to get rid of speed, then you will have a much more survivable outcome. So the bottom line is that your survival is primarily determined by your speed and your angle of impact. So again, the title of this presentation is Surviving Forced Landings. This is really the takeaway, is that you need to understand how to fly your aircraft slowly in an emergency situation. Now, before touchdown, you're going to want to make sure that you and your passengers are familiar with how to brace for impact. There's some question as to what to do with the aircraft doors. The FAA's Civil Aviation Directorate, or the Small Aircraft Directorate, recommends that you keep the doors shut because that would retain the structural integrity of the cabin. However, if your aircraft's flight manual says to pop the door prior to touchdown, then you would go with whatever advice your aircraft manufacturer has used. Also, shut off all the possible sources for post-crash fire, like your electrical and fuel systems. And make sure that your passengers are briefed. Keep them in the loop as far as what's going on, when to brace, and how to open the doors if you become incapacitated. So let's suppose a little bit of a rhetorical question. Which would you rather land in, beans or corn? Corn? Everybody agree with corn? Okay, all right. Well, here's beans. And you can see that, you know, they're real dense and they're kind of tall, and so they snagged the landing gear and he slowed down really fast. All right, so, so beans. What about corn? Well, here he is in corn. There's actually a little story behind this one, though, because this was a gentleman that was flying his airplane. He had put a brand new engine on the plane, and he was breaking it in, and he overestimated his, or I should say he's underestimated his fuel consumption, and he was about 6 miles away from the airport when his engine quit. He was directly over a private landing strip. And he told the approach controller, no, I think I can make it to the big airport. Well, this is how close he made it. Here is the runway. Here's mowed grass prior to the runway. And then he ended up in about the last 20 rows of corn. And it was one of those situations where he was just milking the stick back and trying to stretch his glide, and he ended up stalling and mushing it into the corn and touched down so slowly that the airplane just flipped over on its back. So no injuries in either of those situations at all. It was a very slow speed thing. But it just goes to show, this aircraft was written off, by the way. If he had said, oh, maybe I'll just go for the private strip underneath me, he probably would have walked away from it with no damage to the airplane. Now, here's what I sort of consider to be a textbook emergency approach and landing. Why would I say that? Well, how fast did he touch down? Clearly, it was very little airspeed, because you can see there's almost no corn that was mowed down. It touched down upright. The crew compartment is totally intact. So all he has to do is unfasten his belt and step out of the airplane, and everything's fine. Now, you might say, okay, well, what about trees? A lot of people at these seminars ask me, what do I do if I'm going to land in trees? You might be concerned about that, but even this landing is totally survivable. Why? Well, we see that the crew compartment is intact. This is sort of the common thread to survivability in these situations, is that you keep the crew compartment intact. If you do that, your harnesses and everything will keep you restrained properly. You can see that there were impacts to other areas of the aircraft, but nothing intruded on the crew compartment. In fact, in '98, they did a forced landing study in the Journal of the American Medical Association, and they studied 10 seats or less, and they adjusted the data to remove other variables. And the conclusions were that 62% of the forced landings resulted in no fatalities, or I'm sorry, no injuries at all. No injuries at all. Only 5% resulted in a pilot fatality. So your odds are quite good. And they're even better if you consider what the three major risks for a pilot fatality are, which are fire, explosion after landing, failure to use the lap belt or shoulder harness, or situations where the aircraft was completely destroyed. And again, all three of these items are in one way or another directly controllable by the pilot. Well, we can take steps to minimize the risk of fire explosion after landing by shutting off the master and the fuel systems. Of course, we can take action to use our lap belts or shoulder harnesses. And situations where the aircraft is completely destroyed, what kind of situation do you think that was? The impact, or the speed at impact, was probably very high. So if you take steps as the pilot to reduce your speed at impact, that probably reduces your chance of a situation where the aircraft is completely destroyed. Talk a little bit about survival and rescue. Make sure to file flight plans and stay in touch, and prepare an emergency survival kit to deal with adverse conditions. And keep in mind that a cell phone is great, but it's not necessarily going to get a signal. So you need to think of what your plan B would be if you were in a remote area. Briefly, I'm going to talk about low altitude engine failures. And really, this is the biggest shame of them all, because pilots keep trying to turn back to the runway that they just took off from. And the problem is that few pilots really truly understand what the consequences of such a maneuver are. It can be done successfully, but the circumstances that are required for you to accomplish it successfully are absent. It's not a maneuver that you can practice regularly. There's a lot of variables at play, and you're asked to fly the airplane at the peak of your performance in a stressful situation. And your peak performance might not be there. And so there's a lot of things working against you that would say that you're not going to make this successfully. So first problem is bank angle. If you lost your engine here, and you went into, I think this is a 45-degree bank, they say, okay, you're going to go 560 feet. But if you went to only 30 degrees, it's going to be here. If you went to 10 degrees, it's only going to be here. So you're asked to make a very, very steeply banked turn, which of course is going to drive up your stall speed. So you need to be, you're being asked to make this incredible feat of aviation, and you've never practiced it before. And so what do you think your chances of success are going to be? They're probably not as good as you think they would be. And so if you make a shallower banked turn to avoid a stall, now you're further away from the runway, and you've got to glide even farther to try to make it back. So there's really nothing working in your favor here. Whereas if instead you did this technique where you look in a 120-degree arc, that's a third of the total horizon is 120 degrees, 60 degrees either side of the nose. You should be able to find something in that area that you can put the aircraft in. And as we've said before, you only need about 9 feet to decelerate it if you touch down slowly. So it could be a parking lot or something like that, and you should be able to walk away. In fact, just a couple days ago in Phoenix, there was 2 guys in a 152 that put a 152 down in a playground of an elementary school. There were no kids around, thankfully, but they just plopped the airplane right in. It stayed where it touched down, and they walked right away from it. No injuries and hardly any damage to the airplane. There was actually a scientific study that was specific to turnbacks where the initial success rate was only 42%. And even after repeated practice, the success rate only went up to 62%. Whereas 100% of the straight-ahead landings were successful. So the bottom line is, you're better off trying to do a maneuver that you can do successfully than unsuccessfully. And then the other issue with going back to energy, if you took off into the wind and you're trying to return to a runway, now you're going to be landing with tailwind, right? And we just got through this long discussion about how increased energy is not good for you. So why would you want to be coming back at low altitude in a steep bank with a tailwind and maybe end up in a hangar somewhere? So have a plan for engine failure on departure by reviewing the area beforehand. When it occurs at 300 feet, it's too late to put that plan together. Fight that tendency to turn back after your departure. Familiarize yourself with the safe landing areas that are around, and the bottom line is turnbacks do not increase your chances of survival. Stalling the airplane nearly always kills you. Again, practice. Under periods of high stress, we do not rise to the occasion, you sink to the level of your proficiency. So practice gliding the airplane, practice emergency approaches and landings, and training in these situations is going to allow you to overcome the stress and achieve a successful outcome. What can you do starting today? Get together with your favorite CFI, practice some skills. You may have not practiced these things since you did your private pilot check ride. So get in your airplane and try to practice flying at minimum sink airspeed or best glide airspeed and see what kind of descent rates you get. And practice a low altitude engine failure or a medium altitude engine failure. The conclusions are: be prepared. Don't panic. Know your airplane and your procedures. Know the terrain that you're going to be flying over. And if you have an engine failure, manage the approach all the way down to the ground, including managing the proper airspeed to fly, and touch down as slowly as possible. If you want some more information, there's a good book called How to Crash and Survive. It's at the following link. You could also look at the Flight Training Handbook, which has some good information on approaches and landings. And regarding turnbacks to your departure runway, there's a publication called The Impossible Turn, which is part of the FAA safety program. This is available on the FAAsafety.gov website. And at this time, I would be happy to entertain any questions from the audience. The gentleman in the second row.
Okay. Yeah, let me preface it by saying I don't know if you saw the local news, but yesterday some experimental airplane here that was filming, sounds like you saw it,
Okay.
did a forced landing on a road and rolled off into a parking lot or something, did fine. So my question is, are you better off landing on a road, or should you take that cornfield or whatnot? The thing I worry about a road landing is when you get down low, there may be lines crisscrossing.
Absolutely.
And there's lights and so forth. And if it turns out to be a good spot and none of those obstacles, then that's better. But do you take that chance, or do you take the cornfield next to that road that seems pretty good when you're up at 500 feet?
No, I think your concern is extremely valid, and I would agree with you completely. I think in many cases, a pilot's inclination is to land on a paved surface first, but your concerns are very valid, that there may be power lines or road signs or something alongside the road that are completely invisible from even 500 feet. And you don't want to be in that situation where you get down to 500 feet and you're committed to landing, and then all of a sudden you see that there's a bunch of power lines or something where you can't do anything about it. And so, so your concern is very valid. I think maybe a better choice might be to put it down near a road at the edge of a field, so that you wouldn't have much distance to walk out to safety or anything like that. But yeah, I mean, if it's an area where you absolutely know there are no obstructions, then maybe yes. And we've seen plenty of videotape. Like last year up at Oshkosh, there was a gentleman that landed the T6 on Route 51 or whatever it is that goes past Oshkosh, and that highway was full of cars. And so, I mean, there just happened to be a gap in the cars where he was able to land and pull off to the side of the road. But yeah. You know, definitely any open area where there's no obstructions, like a field, I think would be an excellent choice, because you know that there's no obstructions. And if you've already had a problem with the aircraft where the engines had damage or something like that, are you really going to be worried about some dents to your sheet metal of your airplane from corn? I mean, really at that point, I would be more concerned with just getting down safely and you know, walking away from the situation. Did I sort of address your comments? Okay. Second row.
At no time during this forced landings have you mentioned forced landing in the water. We live here in lots and lots of water, and I've often discussed that point where if I'm near the coast, I'd much rather try to go into the water and not damage property and lose an airplane than. What is your opinion on that?
No, I completely agree with you, and you know, people often ask me, would they rather go into trees or go into water? My preference for that is actually trees over water, and certainly there are plenty of cases where people have ditched into water and they've successfully walked away from it, and that's fine. And I totally understand your concern for property on the surface. The only flip side that I would say with ditching is, again, it's a situation that you can't practice. Okay, so you're hoping that you touch the aircraft down in the right attitude. And commonly, what is most commonly going to happen when you touch the aircraft down? It's probably going to flip. And the windshield may cave in, and you may all of a sudden be faced with an airplane cabin full of water in your face, and you may even suck some in. So you're going to be frightened. You're going to be looking for the exit, trying to figure out how to get yourself out of an inverted aircraft underwater. It can be done. I just say that you're introducing some variables that you can't handle. So that's something you need to think about. I would say yes, nobody wants to make that choice. Do I put it in, you know, the schoolyard full of kids or the lake? Yeah, I'd probably go for the lake. But if it was a situation where there was anything else available to me, like a beach even, put it on the beach instead of put it in the water, because